Hello, welcome to those of you joining us. We're just going to give it a little while here so everybody can get into the webinar, and then we'll get started. Great. Hello, welcome to today's webinar. This is the first in what we're hoping is going to be a great series of webinars that we're planning to do for Earthquake Spectra issues. So thank you for joining us today. My name is Elizabeth Angel. I'm EERI's Communications and Program Manager. And before we get started, I just wanted to take the moment to say a few words about EERI in case you're not familiar with the organization. The Earthquake Engineering Research Institute is the leading nonprofit organization that brings together people from a wide range of disciplines and fields, both in the US and around the world, who are dedicated to the shared task of advancing earthquake resilience. We have members who are students, professionals, academics, people from a lot of different disciplines, and we hope you will consider joining us if you're not already a member and becoming part of the great work that we do here. And one of the most popular things we do, of course, is our peer-reviewed journal, Earthquake Spectra. And so on that note, I'm going to turn it over to the moderator of today's webinar, Jack Baker, who's the editor-in-chief. And I'll just note before we get started that to ask questions of the speakers in this, you can use the Q&A tab on the Zoom control panel, not the chat. Go ahead, Jack.
Great. Hello, everybody. Thank you for joining us today. I'm looking forward to our session. Just make a few quick remarks. So, the last year and a half or so, I've been the editor-in-chief of Earthquake Spectra, and beyond soliciting the best science and engineering in the world and publishing it in the journal, we're always thinking about how we can connect authors with readers as well. And so this webinar is one of the formats we're working on, where we're trying to identify some recent papers that came out, give the authors of those papers a chance to speak in this live format, and give you as an audience the chance to interact with them in a live format as well. So I hope you'll find this productive. Today we've got two papers from the May issue of Earthquake Spectra, and we're going to tentatively plan to identify papers in this way for future issues as they come out as well. Before I get to introducing these speakers that you see up here, I'll note a little bit about the format. So we're going to aim for about a 20-minute presentation from each of these speakers, and then we're going to have a Q&A session for both speakers following that. So you'll have to hold your questions for a few minutes as you're collecting them. But again, I'll encourage you to submit those questions in the Q&A panel. You can submit those live as the presentations are going on, so you don't have to wait 20 minutes before you enter in your questions. And hopefully we'll have a great discussion for the final 20 minutes of the hour here. Okay, so turning to our exciting part of the presentation. So first, I'd like to introduce our first speaker, Professor Diane Moug. She's a professor at Portland State University and working in geotechnical engineering broadly. I'll note, since we're on an EERI webinar, among her awards, she's the 2023 recipient of the EERI Younger Member Award, recognizing her contributions to the Institute in a variety of ways. And she was a lead author on a paper from a gear reconnaissance trip to Turkey following the earthquake sequence there last year, and produced a very interesting paper on some interesting measurement techniques as well as findings from that reconnaissance trip. This was selected as the editor's choice paper from the May issue of Earthquake Spectra, so we're really pleased that she was willing to come and talk about this work here in this webinar format as well. So Professor Moug, thanks very much for joining us. I'll turn the floor over to you now.
All right, thank you very much. And yes, thank you very much for organizing this webinar showcase. I'll be presenting on a paper, Liquefaction-induced ground and building interactions in İskenderun from the 2023 Kahramanmaraş earthquake sequence. And before I begin, I must acknowledge the significant contribution to this work that was done by the co-authors of this paper, as well as the support for this reconnaissance by GEAR, the NSF, and EERI. The 2023 Kahramanmaraş earthquake sequence began with a magnitude 7.8 main shock on February 6, 2023 at 4:17 local time. This was an earthquake event in southeastern Turkey near the Syrian border. And the main shock 7.8 rupture occurred on a fault as a transition between the East Anatolia Fault and the Dead Sea Fault. 9 hours later, there was a magnitude 7.5 earthquake just north of the original event, and then numerous aftershocks in the days and weeks that followed up to a magnitude 6.7. Between Turkey and Syria, the reports are that over 60,000 people were killed from these significant earthquake events. The post-earthquake reconnaissance efforts that we took part in, the objectives of them were to collect perishable data focusing on geotechnical earthquake impacts to infrastructure. And then in the days, weeks, years following this initial reconnaissance, we can then collect more non-perishable data, such as subsurface data, in order to combine that with the reconnaissance data to develop high-quality case histories that are used to inform our earthquake engineering practice and to develop it and learn from it. The reconnaissance in İskenderun, it focused on liquefaction-induced building settlement and building ground interactions, which I'll be focusing on today. There was also reconnaissance that looked at lateral spreading and post-earthquake coastal flooding, and those results are presented in a separate paper by my co-author, Dr. Patrick Basel, also published in Earthquake Spectra. And there's more information on this in the GEAR report that we put together as well. The reconnaissance efforts were, of course, a team effort, and this was an effort by researchers through GEAR, Middle Eastern Technical University in Ankara, Geodestek, and then Zemunash Engineering as well in Istanbul. In İskenderun, there were several nearby strong motion stations that recorded the ground motions. Those are outlined here. We have İskenderun on the Mediterranean Sea, shown by the green star. And I've highlighted the 3 closest seismic stations, 3112, 3115, and 3116. Those stations, we then have the site conditions, the shear wave velocity profiles shown on the right. Station 3112, the blue profile, is the site closest to our reconnaissance efforts in İskenderun. And there is generally soft soils at this site with a shear wave velocity of about 233 meters per second, which we consider to be representative of the areas that we focused most of our efforts. And then stations moving outwards from that, 3115 and 3116, with shear wave velocities of 428 and 870 meters per second, respectively. The ground motion recordings from this site, or from these strong motion stations, are shown in the plots here, with the main shock of magnitude 7.8 on the left. This main shock is what we attribute most of the damage in İskenderun to, and we see the recordings of acceleration, velocity, and displacement plotted here, as well as the response spectra. Unfortunately, the station 3112, the recording shown in yellow, cut off early, midway through that main shock. However, we did collect, the other 2 stations did collect full ground motion recordings. Based on ground motion models for the area, we can estimate that the peak ground acceleration in İskenderun was between 0.2 and 0.4 Gs. Even though this recording did cut off early, we do have some information about the response in İskenderun from recordings of aftershocks, such as this magnitude 6.4 aftershock. And notable from this is that we can see amplification effects within İskenderun at the station 3112 relative to those nearby stations. So we're interpreting that to mean that there were likely amplification effects in from the main shock event as well in İskenderun. The setting of İskenderun, it's a port city. It's a historic port city founded on an alluvial floodplain. Because it's a historic city, we do have a number of historic maps and accounts to help us understand the land development and the subsurface conditions. In historical accounts, it's described as a swampy city. And a lot of the development that took place primarily in the 20th century took place around building drainage infrastructure to drain those swampy areas, and then filling in low-lying land and reclaiming land and building out the coastline as well. We can get a sense of how much of the coastline developed through these efforts based on historic maps, such as this found in a master's thesis from looking at development in the İskenderun area. And we do have an example as well of the historic building out of the coastline. This is a building, a civil registry in the early 20th century. This is a building that we did survey for settlement during our reconnaissance. In this picture from pre-1960, we see that building on the historic coastline. Today, this image from Google shows that there's been development and reclamation of land in front of that building. Currently, Ataturk Boulevard runs in front of it. And then there's about 100 to 200 meters of additional land built out in front beyond Ataturk Boulevard. And Ataturk Boulevard is considered for a lot of İskenderun to be a delineation or to run along that historic coastline area, giving us an idea of where the land was then built out from. Reclaimed land is also shown by comparing these aerial photos from a recent publication by Tafskalu et al. And we can see the coastline in 1969 compared with the current coastline, and again, getting a sense of how the land has been built out in İskenderun. We have some subsurface conditions in the area based on an engineering report by Denge Engineering from 2011. I'm summarizing the results of 3 boreholes in the areas close to which we performed reconnaissance, as shown in the map down in the lower left corner. Generally, what we see in the subsurface conditions are at least 30 meters of very loose to loose silty sand with low SPT blow counts. And water levels between 1.5 and 3 meters depth, indicating a shallow water table. Conditions that are susceptible to liquefaction of loose sandy soils and a shallow water table. Recently, in March of this year, our colleague, Dr. Fikret Adale, he traveled on behalf of our team through an NSF Rapid grant to collect some of that subsurface data at sites of reconnaissance. And this isn't included in the paper, but I'm including it here as additional information and context for the study of taking these CPT data and looking at CPT-based liquefaction triggering analysis, in this case from the Boulanger and Idris 2014 method. Using those ground motion characteristics from the magnitude 7.8 main shock. In these 3 profiles from the areas of reconnaissance, we see sandy soils that are susceptible to liquefaction triggering with these ground motion demand parameters, with factors of safety against liquefaction triggering well below 1 and near 0.5. So again, confirming or providing additional evidence that that main shock was the likely trigger of liquefaction in the area. A summary of the reconnaissance summarized into this map figure of İskenderun. The reconnaissance tracks are shown from our teams in the dashed black line, and then areas of major liquefaction as evidenced by observation of ejecta, shown by the green triangles, or building settlement. That area is outlined or shaded in with the orange color. And we see that this is largely associated with the historic shoreline and reclaimed land, where the reclaimed land delineation based on historic maps is the dashed area or the hatched area here. And the blue line is Ataturk Boulevard, again, that delineating the historic shoreline. As we move away from the historic shoreline and away from reclaimed land, there was less and less evidence of liquefaction and liquefaction-induced building damage. The reconnaissance efforts that our team performed included, for surveying building settlements and ground deformations, included laser level hand surveys, as shown in this upper left-hand picture, where surveying building settlement relative to a point where the ground was considered not to have been affected by liquefaction or not to have settled. And then also terrestrial LiDAR scans, as shown in the lower left-hand corner. By combining this data, we could get a more full picture of the building settlement and the ground deformations around the building. We're showing building B in the Chai district as an example here of those 2 methods of surveying. With the LiDAR data scan and model that we built in the lower center figure. And with the LiDAR data, we could then take that data back to the office and continue to analyze and reassess that data from our desks and tie it into the hand survey data and the photos. This picture is showing the building and then also the contours of ground deformation, seeing that the ground settlement was highest closest to the building, as we would expect. This building had an average settlement of 400 millimeters as determined by the LiDAR data. And then again, we found the LiDAR data to be more reliable due to reassessment that was possible. We see some discrepancy between the hand survey measurements, particularly on the east side of the building. And this speaks to the challenges with hand survey data of tying together all four corners of the building with a single data reference point. The reconnaissance that was performed focused on two main areas, the Yenisheir district and the Chai district. In total, there were 26 buildings surveyed during this reconnaissance effort. And generally what we see is that the settlements decreased inland from the historic shoreline and were most severe along the historic shoreline and on reclaimed land areas. In the Chai district, 12 mid-rise buildings were surveyed. These are 5 to 6 story buildings that had a settlement of 240 to 740 millimeters of settlement. There were also 3 high-rise buildings that we observed where we did not observe any liquefaction-induced settlement. And we're assuming that these are on pile foundations, given their relatively strong foundation performance and the poor ground conditions in the area. There's also a single-story building that we surveyed that had 220 millimeters of settlement. And further in this presentation, I'll go into some of the mechanisms and interpretation of what might have induced this settlement at the single-story building. In the Yenisheir district, shown up here in the upper left-hand, we surveyed 10 buildings with settlement between 0 and 500 millimeters. The settlements in the Yenisheir district were largest along Ataturk Boulevard and the historic coastline, and then decreased as we moved away from Ataturk Boulevard. This building here had relatively strong performance of 60 millimeters of liquefaction-induced settlement, and then evidence of liquefaction decreased away from the historic shoreline. I'm including some examples of typical building conditions and construction in the Chai district, where so much of our reconnaissance was focused. These are 2 mid-rise buildings, 5-story buildings, with reinforced concrete frame and infill wall construction. Building D on the left had a settlement of about 310 millimeters. This building, based on building plans we were able to obtain, had a mat foundation at 3.4 meters depth. And then above that mat foundation, the subsurface was developed half into a basement and then the other half backfilled with soil. In building C, which had a settlement of 500 millimeters, the foundation conditions did not have a basement, and the foundation was made of strip footings in orthogonal directions. What I'm going to focus on for the rest of the presentation are interactions that we observed between buildings and ground. And I'll be looking at 3 cases in particular of hogging ground deformation. And hogging ground deformation, as we observed it, is building settlement, liquefaction-induced settlement of the building that dragged down or appeared to drag down the ground for several meters around the building in a convex-like pattern. So we had a bending down of the ground complementary to the liquefaction settlement that was induced. I'll be looking at 3 specific cases of this, 1 case in the Yenisheir district, and then 2 cases in the Chai district, the case of 4 buildings in the Chai district, and the restaurant case. Like I said, there are 3 cases we're looking at, but we do believe that there were likely similar building ground interactions throughout İskenderun and the Chai district. However, access to buildings, obstructions, building spacing, and just time did not allow us to make other observations of this. Looking at case 1 in the Yenisheir district, there was this hogging ground deformation that occurred between 2 buildings, this building with 420 millimeters of settlement and the building on the right with 450 millimeters of settlement. These buildings were spaced 29 meters apart, and the hogging ground deformation extended about 10 meters from either building, resulting in about 9 meters between them that appeared unaffected. And this is further supported by this building, a kindergarten in the middle of this hogging ground deformation that did not appear to have any type of ground building interaction to it or induce damage. So as we interpreted this case, we see the hogging ground deformation induced by the buildings on either side, and then the zones of influence from these two buildings not overlapping, and there being unaffected ground between them. Moving to the second case in the Chai district, I'm showing images taken from the LiDAR scan in the middle of the courtyard at the rear of these four buildings. We can see that there was liquefaction-induced settlement at these four buildings, which is accentuated by the flood waters that have pooled at the base of these buildings. We can see the curvature of the ground that is again further accentuated by pulling apart and deformation of the ground pavers. Within this courtyard, the buildings settled between 390 and 750 millimeters. And we can see that from the LiDAR scan, we are able to observe the contours of the ground deformation, seeing that it extended across the courtyard. From the LiDAR data, looking at the ground deformation across 6 different cross sections, we can further see the deformation that extended across the courtyard by plotting the settlement versus the distance from the center of hogging. The LiDAR ground data are shown with the open symbols, again showing that hogging convex pattern of ground deformation. Building settlement plotted on this as well shows a consistent pattern with the ground deformation, giving us further evidence that the ground deformation is induced by the building settlement, or that there's interactions between them. There was about 100 millimeters of settlement at the middle of the hogging, where the middle of the courtyard had been dragged down as well. And this is interpreted in this case as overlapping zones of influence from the ground deformation of buildings on either side of the courtyard. And understanding that there is overlapping influence in this case gives us more information to interpret the third case. In this case, we have two mid-rise buildings on either side of a single-story steel frame building, with 400 millimeters on the left side of settlement and 510 millimeters from the building on the right side of settlement. And it appeared that the hogging ground deformation from these two buildings was overlapping and affected the building in the middle, the single-story building, that appears to be distorted and damaged by the hogging ground deformation. And we have settlements that also show that pattern in the building, or larger settlements at the edges and less in the middle. The damage at the building was observed through tension cracks in the title sign, tension crack in the retaining wall at the front, as well as tension cracks that run through the concrete slab of this building. And I'll accentuate them here in red. We also saw that when we plotted the settlement and deformation in this restaurant case of the buildings and the restaurant and compared them with the group of 4 buildings, we see a similar ground deformation pattern here, indicating that the restaurant likely had minimal constraining effects on the ground, and that there appears to have been a characteristic ground deformation pattern in the Chai district, which we are planning to investigate further its mechanisms and influences and interactions with nearby buildings. And so our conclusions from the study is that we observed widespread liquefaction in building settlement in İskenderun that was associated with reclaimed land and the historic shoreline. Liquefaction-induced building settlements ranged from less than 50 millimeters to 750 millimeters. And there was also cases of hogging ground deformation among several buildings. And in at least one case that we observed, this hogging ground deformation led to damage of an adjacent building. And I'll say thank you again for this opportunity to present this work. And I look forward to the discussion and questions that follow.
Great. Thank you, Diane. That was excellent. Very interesting work and very nicely presented. Maybe before we shift, I'll take the liberty of maybe asking one quick clarification question, looking at what came in. There was a question about these buildings in these case studies, case 3 specifically, but maybe more generally. Were there basement levels in those buildings? And is there anything relevant about that you might comment on?
So yeah, the basement question is one that we're still working on. In case one of those buildings does have a basement and the other doesn't. And so that's sort of one of those, we saw similar interactions and we saw similar settlements from them, but one had a basement, one didn't. In the courtyard case, I think it might be a similar case where there was at least a partial basement in two of the buildings and not in the others. And then with the third case, I don't recall there being a basement in the building on the left. The building on the right, we did not have good access to. That's why we only had surveyed settlement at one corner. So we weren't able to go in and see what was happening. But yeah, I'll make this brief, but I'll say that in the Chai district, there were basements. They weren't very common, but there were basements. We were actually surprised there were basements because the water level was so shallow in that area.
Great. I see at least one more question about this general topic, but I think let's save for a longer discussion. Appreciate the chance to get that clarification. Thank you again. Okay, and yeah, a reminder to our audience, we'll have a further Q&A coming up in after the second presentation. And so please think about what you might want to discuss and drop any thoughts or questions into the Q&A box that's available to you here. Okay, so I'd like to shift to the second presentation for this webinar now, and we'll do that presentation. So we next have Professor Vitor Silva to present. He's a professor at the University of Aveiro in Portugal, as well as the risk coordinator for the Global Earthquake Model, GEM. In the spirit of highlighting our EERI activities here, I'll note that he is an associate editor at Earthquake Spectra and has been for a number of years. He's also the 2017 recipient of EERI's Shaw Prize, recognizing his achievements and entrepreneurial efforts related to seismic risk. So then I'll note just briefly, so this second study here, as well as published in the May issue of Earthquake Spectra, this is a data paper. And so we wanted to take the chance, one, to highlight this data paper category. It's a category of the journal that's growing in popularity, a chance to archive and discuss and document data sets that might be of broad interest to the community. And so keep an eye out for those data papers. We thought the webinar on this one specifically would be a good chance to expose our readership in more depth to the data set. And I'll just note, personally, I found the data set to be really interesting. And those of you who are on the call who are professors or working with students perhaps have the experience I do of many students coming by looking for data sets that they can learn about to machine learning algorithms and image classification algorithms and things like that. And so I immediately saw this data set and thought I'm going to pass this on to some students as a chance for them to explore all of these new algorithms that are very of great interest in various parts of the world as they develop. So with that, Vitor, I'll turn the floor over to you to give us some discussion about this paper. Thanks for joining us today.
Thank you very much, Jack, and thank you very much, EERI, for the invitation. Always a pleasure. So for this particular paper, this is a data paper, so I just included a little bit more detail about the context and how I think like some of these data sets might be used, because sometimes there's not much to talk about a data paper because it's typically just data and there's not a lot of research there. But just to provide a little context, I've been exposed to a lot of applications of seismic risk studies, seismic risk results throughout the years. Like, for example, initiatives to distribute funds for risk management, the development of insurance products, the assessment of investment needs from global organizations like the World Bank, the United States Agency for International Development, or the European Union, the development of preparedness and response plans, design of large-scale retrofitting campaigns, and then, of course, also training and educational material. And something that I noticed a lot of time was that some of these data sets that were being used by taking these decisions that a lot of times involve millions and millions of US dollars were quite coarse. They were quite rough. And sometimes a lot of decisions were being made almost at the local level, sometimes almost at the building level, with a lot of data sets that, in my opinion, needed to be rather optimized, and we need a little bit more detail, both in the attributes, vulnerability attributes of the building, but also on the location. When we run these risk calculations and the way that we are using, for example, the data from this data paper, we do need to assess seismic hazard, either from earthquake scenarios or probabilistic seismic hazard, for example, using stochastic event sets. We need to understand where's the location of the buildings, and this is typically included on the exposure component of this problem. So we need to know, for example, the latitude and longitude of these buildings to properly calculate the source to site distance. We bring vulnerability, and then we calculate the impact. For example, buildings lost, area lost, economic losses, fatalities, or homeless. But the problem that a lot of times we have is this. For example, this is the current exposure model that is being used for risk analysis in Spain within both the global earthquake model, but also in this European project that just finished a couple of years ago. So we do have good information, but only at the first administrative level. So this is rather coarse, because then we need to either aggregate all the buildings in a particular location, for example, the major city, or based on the density of the buildings, or we need to spatially disaggregate the buildings. And there's a bunch of techniques to do that, using satellite data, using OpenStreetMap, but there's limitations, and this will always add a necessary bias and uncertainty in the risk results. Also, something that I typically try to show to my students when I'm asking them, you really need to improve the spatial resolution, the detail of these models, is, for example, this image from the Kashmir earthquake in Pakistan. We can see that all the buildings on the top of the hanging wall are heavily damaged. Most of them have collapsed. But then we see that the buildings on the left of the fault rupture, which is marked here in red, I'm sure they're also damaged, but at least we can see that the rate of collapse is much lower than what we see on this other side. So, for example, using the example I just gave from Spain previously, aggregating the buildings on the left or on the right could lead to very different types of results. In particular, for example, if ground motion models that can take into account the position, for example, if it's on the hanging wall or not, are being used for the risk calculations. So for this reason, we've noticed that, at least in my opinion, and this is a very personal opinion, despite the fact that in the last 10 years, I had used a lot of data sets from housing census, from OpenStreetMap, from all these different data sets, I think the future is not there. I don't think that's how exposure model in the future is going to be done, and not how a lot of this risk assessment and risk studies and risk applications I was describing previously should be informed. We now have a lot of information from initiatives like, for example, Google Street View, a lot of information, a lot of imagery, for example, from drones, which have been used for different purposes. And we also have all these different algorithms which can rapidly recognize images and particular features of buildings. Some of these algorithms have been developed by other purposes, like, for example, to detect cancer, to detect even stars. But a lot of this algorithms, this technology is being applied now to detect buildings, architectural features, or, for example, damage after earthquakes. I'm just showing here some examples of this, of one of these algorithms, which is called YOLO, You Only Look Once. But I was quite impressed to see that basically using this large data sets of people, of cars, it is possible for these algorithms to rapidly detect if it's a building, if it's a person, if it's a motorcycle. So I really thought, okay, we need to start applying a lot of this technology to exposure modeling. I think this is going to be extremely useful for earthquake engineering. So typically how this works, in order for us to train these algorithms to automatically classify building classes, is we need to have a large set of images to train the data sets. For example, a convolution neural network. We train the algorithm. We need to have a lot of images that have not been seen during the training phase. And then we test the algorithm with these images that have not been seen by this framework to try to estimate if the buildings are being properly estimated or not. We wrote a grant to the Portuguese Foundation for Science and Technology. We presented this idea, we were successful, and we decided then to start collecting data to test these algorithms, but then to put all this data in the data paper that has been published on Spectra. We chose this parish. This is located within the district of Lisbon in Portugal, the capital. This is a rather interesting district because it has been heavily studied. So we did have a lot of information about the buildings, even some drawings. And this is actually an area that covers both recent buildings, old buildings, masonry, concrete, so a lot of different typologies. Even covers also, for example, sports centers, a university, a national laboratory of civil engineering, a hospital, and so on. And again, you had a lot of types of construction, and we wanted to make sure that we're going to collect photos that would be useful for Portugal, for urban centers in Portugal, but in a lot of parts, for example, throughout Europe, in Spain, in Italy, a lot of the buildings that exist in Portugal, they do have some similarities with types of construction in other countries, so this could also be useful for those countries. So we divided this region in three, and this was because we had three master students, civil engineers, that were going to be collecting the data. We wrote an algorithm that basically divides the region in the same number of buildings. So in each one of these polygons, we have more or less 1,000 buildings. And then this was further split because basically in each day, the student was able to collect about images and classify 100 buildings. So for each one of this building, we collected this type of information, material of construction, number of stories. We tried to collect as much as possible also the age of construction, OF of construction, structural system, similar irregularities, the type of roof, number of windows, balconies, and if there was a basement in that building. To classify each building, this is actually quite important to emphasize. We try to use as much as possible a uniform classification system. We use the GEM taxonomy, which is basically a way to classify the buildings in a uniform manner. It's almost like coming up with the DNA of each building. It has 14 attributes. We did not use all these attributes because some of them were not relevant, or it was just too cumbersome to collect all this information. But we were pleasantly surprised that before we even started this study, there were already another 2 studies that use exactly the same approach, and they use the GEM taxonomy. In this first study by Daniela Gonzalez, they collected information, images from 10,000 buildings in Medellin, Colombia. And in this other study by the colleagues from Germany and Chile, they collected information and images from 27,000 buildings in Santiago de Chile. And again, they use this approach, the same methodology, the same taxonomy. Later on, we also noticed there was another study for Oslo in Norway, where again, the same classification system was used. I'm just emphasizing this part here because actually I contacted the authors of these studies and I told them, look, we should actually merge all of our images and just start creating this big open online database of photos of buildings that have been classified. And if we use the same classification system, the same approach, then we can merge the entire data set. And we can start, hopefully the scientific community then can use all this data to calibrate machine algorithms for other parts. So just to summarize the process that we follow, so there's a lot of desktop planning. Before we send the students into the field, it is important to make sure that each one of these buildings has a building footprint, and we leverage on OpenStreetMap. A lot of the building footprints were already there, but we also had to edit OpenStreetMap to add additional building footprints, and sometimes we had building footprints that were covering many buildings. We divided the region, as I mentioned previously. We sent civil engineers into the field to collect building by building information. And then we build a user interface for quality control. And we hired also an earthquake engineer to verify building by building to understand if there were some obvious mistakes that were done and if we needed to include some additional corrections. So this is the database that we have now. So it's 3,000 buildings. This is the distribution of the buildings by type of material. This is by the number of stories, and this is by the age of construction. In addition to be able to classify, to develop machine learning models, and I will show in a second an application of exactly that, we also noticed that this is actually extremely useful to develop spatial correlation models for exposure models. So in the same way that we have spatial correlation models, for example, for ground shaking, for the ground shaking residuals, we can also basically come up with some anchor points, places where we are sure about the building typologies, and then based on the distance to these buildings, we can start sampling what is the most likely building class surrounding that building. All the data has been put on Zenodo. It's both on Zenodo and also on GitHub. So we included all the images. So it's more than 5,000 photos of buildings, both from OpenStreetMap and also the photos that we're taking on the street by the students. And then also there's a CSV file that includes basically the file name and then all these attributes that I was mentioning from the Gen taxonomy. So with that information, it is possible to train machine learning algorithms, but it's also possible to use these data sets right away for example, risk analysis, because we have the location, we have all this information to classify the buildings. Also, something that I would like to mention is that training these algorithms is extremely important. For example, for phenomena that is not necessarily ground shaking. We just saw a presentation from Diane about liquefaction and how important it is to know exactly where some of the buildings are because of liquefaction might be an extremely localized hazard. We've seen this also for landslides, and a lot of the data that GEM produces is also being used for flood modeling and for some of the volcanic hazards. This is just a very brief demonstration of the database. This is not included on this data paper, but I just included 2 slides to show how this data can be used. We trained 6 machine learning algorithms. This is a confusion matrix. So if the model was perfect, basically we would have only occurrences on the diagonal of this matrix. We can see that it is quite good. 85% of the cases, it managed to classify the buildings, but we can see that there's also some cases where the algorithm did not manage to predict the variable. But something that I want to show is actually an application of a model that has been now developed and used for impact assessment for an earthquake scenario close to Lisbon. The result that you see here on the top is the results using the true data. So basically the classification system, the classification that was done by the students on the field and then further verified by the earthquake engineer. The results that you see here was calculated using the exposure model that was developed, that was completely created by the machine learning algorithm, the best machine learning algorithm. And we can see that the errors are extremely small for the different damage states and also for the different injury levels. And the reason was because even when the algorithm was making some mistakes, it was not confusing a modern building, a high-rise modern building with, for example, an Adobe building of 1 story. It was making mistakes, for example, with a number of stories. Maybe it was 5 instead of 4. Or, for example, it was making some mistakes about when the building was constructed, but typically not that it was extremely old or extremely new. It was just a few apples of difference. And with that, I would like to thank very much EERI once again for the invitation.
Great. Thank you very much, Vitor. Appreciate that that recap and documentation of a very interesting data set. Okay, so we have a few minutes remaining on the scheduled hour here for some Q&A with our authors and presenters. So I'll encourage the audience again to submit your questions through the Q&A portal. And I'm going to start asking some questions off of that list that have been coming in over the first 40 or so minutes of the session. And I'll come back to Diane here to start. I think the audience has had more time to think about questions there. So we've gotten some other questions again about kind of subsurface conditions in the buildings and surroundings. So maybe I'll start with a paraphrase here, I guess, a more general question about the foundations, and I jumped the gun a little bit with the previous clarification. But I wonder if you could speak more generally about what you know about the foundations of these buildings that you were studying.
Sure. So as far as we know, and I think we have pretty good records in this case that none of these buildings were on pile foundations. If they had basements, they were partial basements. And whether the foundation beyond that was like strip footings or a mat foundation, there was likely some combination of those at the buildings that we observed. I believe that we have building plans incoming for several of these buildings. And so again, that goes back to the building up the case history data and understanding these situations better as time goes on. There was also a question about ground improvement in the area. And I don't have a full answer for that, but I think from our colleague that went there to do the CPT data, he's Turkish, which was a big advantage because he could talk with folks and learn more about what was happening. And I think that there was mentioned that there was a lot of jet grouting that had taken place in the area, but I don't have I don't have good information right now about the state of ground improvement in the area. I will say, and this will be kind of the last point that I'll make here, there was this building in the Chai district that that we surveyed, and this building did have a full basement on concrete piles, a mid-rise building, similar construction to the other buildings in the Chai district, and on liquefiable ground, and ground that did liquefy, I think we can pretty confidently say. But this building did perform relatively well. There were about 230 millimeters of settlement observed at this building, but performed notably better than many of the other buildings within the area and similar building types.
Great, thank you. Let's see. Another question about this study area, and you had some very nice maps of kind of the reclaimed land and where you saw liquefaction. There's a question about, were there areas of reclaimed land that didn't have liquefaction, and were there any observations you had? You mentioned ground improvement a little bit, but I wonder if you could comment more there.
Sure, happy to. So I'm going to go back to a figure. I think that was David that asked that question. And so I'll flip between two figures here. One is, I think that these aerial photos from that publication that did some remote sensing analysis of liquefaction, something that I found notable with these photos is that there is all this reclaimed land in this area, from which there were few observations of liquefaction. Our reconnaissance team did not specifically go to this area, and I know that a previous reconnaissance team, they drove through that area but didn't see evidence of liquefaction. So there was potentially this area that there wasn't severe liquefaction damage. And I think when we go back to looking at the observations made by initial reconnaissance teams, that there is just less evidence over here of liquefaction. And it becomes a bit of a chicken and an egg. Like, did we not go there because there wasn't reports of liquefaction, or did we miss, which to me seems likely, versus there being liquefaction and us not observing it.
Great. Maybe I'll take the liberty to follow up. Do you have any sense of like the timing of the fill, or is the age of that kind of area off to the west similar to the area where you were doing your reconnaissance, or do you know? I
think that so we have those historic maps from the 20s, and then from the 1920s, and then the aerial photo from 1969, which has proved to be fairly useful for understanding the age of the fill. And so it looks like a lot of this fill has been placed since the 1970s. Beyond that, I think that the Chai district has been filled in a little bit more recently than these other areas, but a significant part of it seems to be post 1969.
Great. Another question for you, Diane, is about these observations of hogging and the zone of influence from the buildings, and a question about, is this a phenomenon that's been seen broadly in previous liquefaction reconnaissance efforts, or how does this fit into kind of the historical understanding of these phenomena?
Yeah, that's a question that we've had discussions on within our group. Based on previous reconnaissance, we were not able to pull any similar observations of this kind of deformation. Professor Jonathan Bray, who's been heavily involved in geotech reconnaissance, this was the first that he had observed this. However, I will point to Professor Shadade Ashti at University of Colorado Boulder, has been doing centrifuge and numerical analysis of building interactions. And she has observed, she presented this at the annual meeting, observed similar ground deformations in their group's numerical analysis between buildings. So there is potentially, this could be a case where we go forward to the numerical analysis to further understand this.
Great. And then a final question for now on this liquefaction study, but maybe I'll phrase it generally as, do you have thoughts on kind of general recommendations that might come out in terms of kind of building design? There was that specifically raised about spacing between buildings that might be informed by these observations.
Yeah, I could see that further studies helping us to understand when interactions between buildings need to be considered. I think that would be the first case of recognizing when we need to consider them, and then how buildings are interacting with each other. Again, I'll point to Professor Dashti's work showing that ground improvement at one building can have an effect on another building. And I think that her work will really be a path forward for these type of recommendations.
Right, thank you. Maybe I'll turn to Vitor for a little bit here. So we have a few questions here. So one, you raised this interesting context about these other data sets from other countries using similar classification schemes, and the questioner was interested in kind of if you could comment, or maybe I'll ask if you can comment on what might change as you're trying to look at kind of multi-country data sets with different types of construction versus I'm guessing the machine learning statistics you were presenting were Portugal specific predictions. Could you comment on that?
Yeah, it was for Portugal, and we had calls with the people that develop, the other models, and I was quite excited because I was like, let's just merge everything. But then we started looking at the data, and for example, reinforced concrete for Chile, even for houses, because seismic hazard is so high, quite commonly everybody uses shear walls, even in houses with 1 or 2 stories. And then we look at the data set, for example, for Colombia, still South America, but that was not the case. It was very common that it was just moment frames with infill panels. So I thought, it's nice if we have more data available, but we have to be very careful about what we're going to use to train our model. I will use that, Jack, also to answer, the question of Professor Eduardo Miranda, because he's also talking exactly about that, the lateral resisting systems. And with reinforced concrete, typically we have moment frames, shear walls, multiple systems. And it is, I'm going to say, virtually impossible. From the outside, you're not going to see like a lot of the structural elements. What is typically a good indication, what we noticed when we were classifying these buildings, a good indication is typically, certain architectural features. If the building is quite modern, and if the building is tall, there's a higher likelihood that we're going to have dual system or shear walls, okay? If the building is old and is 1 or 2 stories, there's also very likelihood that it's going to be a moment frame. So sometimes it was quite interesting. Also the same thing, for example, between unreinforced masonry from the 60s and reinforced concrete from the 60s. Buildings that had a lot of balconies and openings, and obviously the model can detect this, was more likely to classify that building unreinforced concrete than unreinforced masonry, for obvious reasons that the unreinforced masonry was not capable of sustaining such stresses. So a lot of times I was very impressed to see that the machine learning algorithm was actually finding patterns and drivers that I was not finding. And then I learned with all these data sets to understand that it was probably not seeing certain, structural features, but it was using other architectural features, the way that the building looked from the outside, to basically try to infer other things that we cannot see from the outside. But I would say that, because there's also a question here about should we apply this in other countries, I think I would not apply the algorithm that has been trained, for example, for Portugal directly for Spain or Italy. I could try to use some of the images that were collected, for example, for Portugal. If I know that these building classes exist in the other countries, then I would train the algorithm again only with subset of images that I know that exist in these countries, and then I would feel comfortable in using, those machine learning algorithms.
Great, thank you. I think it's probably mostly clear from context for the audience, but just to make sure there was a related question that we all can see around potential errors in classifying the systems that aren't visible from photographs. So that's that extra context there that Vitor nicely filled in. Let's see, another question for you, Vitor, maybe a couple related to the, I'll ask one first. So you showed this data set of the imagery and the building characteristics, and then you showed some risk analysis results. Is the data related to the broader inputs for the risk analysis results? Is that part of this data set, just to clarify, or was that kind of a follow-on study that built on this data?
It was a bit of a follow-on, but I'm actually very glad you're asking that, Jack, because yet another advantage of trying to use a uniform classification system for the building is that then you can connect your buildings that you have classified to all these resources that exist out there, from fragility functions, vulnerability functions, damage databases that I have used also that classification system. So there was also something that we're looking for. I see the function, the question about fragility. We use a probabilistic approach, of course. We use cloud analysis and many ground motion records and linear time history analysis. It was not part of this work. It was fragility functions that existed already. But it was very easy for us. I think we ran the earthquake scenario like in an afternoon because everything had been already classified. All the components were speaking the same language, so it was very easy to start testing the model.
Great. Another question for you, Vitor, about this prediction of the building characteristics that you showed some statistics on. Could you comment on the algorithm that you used for developing that predictive model or training it?
Yeah, so we use convolutional neural networks. We use 6 algorithms to train this. I don't remember exactly the names. That's in another publication, which is more on the computer science world. It's in another paper. Quite happy, to share that, or maybe even because we're also planning to share the algorithms. Okay, so if anybody wants to use this is also going to be in a public repo. But I don't remember exactly now the names of the 6 algorithms that we use.
Great. I'm going to ask a couple of my own, out of my personal curiosity. It was interesting to hear your breakdown of kind of how you identified people to be going out and collecting this data and doing the verifications on the data quality. I'm curious, do you have a general or like an estimate of how many person hours in total went into the data collection effort and curating this data set?
We definitely underestimated the amount of work, okay, because we had this project, we actually had a budget, to pay for the students. Okay, we did not abuse of the students. We had some funds for the students to go and try to collect all this data. I think I had anticipated that they would need at least 2 weeks because I thought that basically each region was going to take only 1 day. It's 100 buildings, but sometimes it was quite complicated. We talked with one of the students, and for example, people might not like that you are in front of their building taking photos, right? So there was a situation in which people came and asked, why are you taking photos of my building? So this was something that we're not considering. And then the student said that he had to leave and he had to return on another day to do this. This was something that we're not taking into account. But for my estimations, I thought it would be like 100 buildings per day. We were also not very good with the technology to collect this because then as part of another parallel initiative, we actually developed an app, just a phone app to facilitate the entire process. But before we were doing work in a very manual way, we were filling in a Google spreadsheet, and that was definitely not a good approach. I think now that this app exists, there's all these different tools that exist already out there. I think would probably take a little bit less time, but I would say per surveyor maybe 100 buildings per day.
Okay. And then but you also have these kind of follow-up quality control checks and things like that. Was that a substantial amount of the project time, or did that go faster than the field work?
It definitely did not go faster. So this is also why we created the interface, because you go building by building. But sometimes, for example, I show a pretty photo, but a lot of the photos were taken from Google Street Map. I didn't include those photos there, but sometimes you have a car passing by, you have a tree, you have like all these different things. And on this interface, it was possible for you to actually click on the link to the Google Street View, and you could see the building from different angles. So sometimes the person doing this needed to also verify this. So it was a little bit of work. I will say, however, Jack, that the way that I think this might be done in the future is, for example, let's say that now I'm going to apply this in another district in Portugal. I can actually use this algorithm to pre-classify all the buildings, and then it's less work because somebody goes there and says, oh, this algorithm, and I know that is high likelihood the answer is going to be 80% correct. So then it's just a process of trying to correct everything that has been classified as opposed to classifying each building from scratch.
Thank you. I think for both of you, it's really interesting to see the insights from the work, but also to see some insights about how the work was undertaken for people thinking about similar efforts in the future. So we're coming up on the hour, so I think I'm going to turn the floor back over to Elizabeth here to have a few concluding comments. But I'd like to once again thank our presenters for some really interesting presentations and associated papers, and also thank the audience. It's great to see a large audience here today and active questioners following up. So I'll take that as a vote of confidence that this is a productive effort for our society. So Elizabeth, I'll turn it back to you to close things up.
Great. Thank you so much, Jack, and thank you again to our speakers. I just wanted to thank everyone for attending. Stay tuned for more upcoming webinars. We have one next week on the earthquake that happened in New Jersey this spring. So that should be an area we don't often hear quick quake briefings about, hosted by our Northern California chapter. And of course, we plan to do another one of these for the next issue of Spectra when it comes out in August. And there are a few more great programs in the works. So stay tuned. You can find out more about those on our website. We also encourage you to become a member of EERI, and you can help support our work by donating to the LFE endowment. And then finally, I wanted to ask people to complete the webinar survey. That'll pop up in your browser after the webinar ends, and you'll also get it by email tomorrow. That helps us understand better what kinds of things you're interested in. And finally, just to thank FEMA and EERI members and donors, the LFE Endowment Fund, for help making this webinar program possible. So thank you very much, and we look forward to seeing you at our next event.